Hey guys, welcome back. Today we're going to be talking about volcanoes and the study of volcanoes, which is called volcanology. Um, right to start off, we kind of have three iconic images of volcanoes as we know them. This one is probably my favorite of the three, and then of course this one here. And notice that we see out of the top of this very tall mountain, these gullies are actually on the side of the mountain. This is a very tall mountain. The same thing here. That we have this huge ash cloud, which is actually larger than the mountain, coming off and spewing hot material all over the place. We're going to call that pyroclastic material a little bit later on in the lecture. The same thing is happening here. Here's a huge eruption where the ash cloud is actually rising all the way up into the stratosphere. Look at the cloud that is actually forming around the ash. There's cloud around here. It's actually burrowed a hole right through the cloud layer, and around it has a little section of cloud immersed within the eruption. Here we actually see a different type of eruption. This is a basalt flow that's coming out. It's hitting the road, and normally lava is not on fire. And in fact, the lava itself is not burning. What it's doing is it's burning the road. The road has tar in it. Tar is a hydrocarbon, just like diesel or anything else is, and it's burning it and creating black smoke as it goes across this road. Now notice that there's very big differences in the types of eruptions you see here, right? Here we see a big ash cloud coming up to all the way into the stratosphere. Here we see a nice lava flow that kind of comes down. Somebody can actually stop and take a picture. You would not want to be on the side of this taking pictures. You'd want to be about as far away as this photograph is taken, and probably not much closer. It's very, very dangerous to get close to these. But this lava flow you can come right up to on the road, and you can take pictures of it. What makes these different lava flows occur, or what makes these types of eruptions occur? Is it the chemistry? Is it the type of volcano? Is it something else? Well, the answer is that it's really a combination of all three of those things. So we need to use what we've learned in the previous lectures about igneous rocks and chemistry and the origins of magma to be able to understand why volcanoes behave the way they do and create the rocks that they do. So there are several factors in determining volcanic eruptions. First off, the degree of explosiveness is something that we should probably get out of the way right away. So there are factors that determine the amount of violence or explosiveness of a volcanic eruption. The composition of the magma, the temperature of the magma, and the amount of dissolved gases in the magma. Right, so the composition of the magma, this is our old chart that we've been using several lectures now, right? There's volcanic and plutonic or intrusive and extrusive. This would be the extrusive, this would be the intrusive. The silica rich would be the rhyolite, pumice, and obsidian. The plutonics would be granite. Same thing with the intermediates, andesite, diorite. And the silica poor, the mafic rocks, would be basalt and gabbro. This is an apparatus that's used to actually measure the temperature. This is actually used to measure the composition of the gases. So you'll see there's a gas cloud coming out over here. And this has the ability to remotely measure this. You would not want to be breathing this stuff in. There could be very dangerous chemicals in there, such as sulfur dioxide. And this scientist here has, I believe this is a thermocouple, is actually measuring directly the temperature of the lava by sticking this probe right into the lava and getting a measurement of its temperature. So these three factors control the viscosity of a given magma, which in turn controls the nature of an eruption. So really the main issue here is viscosity. Remember, viscosity is the stickiness of a magma, how sticky it is, not only to other things, but to itself. So just as we just said, viscosity is a measure of a material's resistance to flow. Ergo, higher viscosity means materials flow with greater difficulty. Factors that affect viscosity are temperature. So hotter magmas are less viscous, for example. So here we have a nice photo that demonstrates this is a gel that is being poured out at different temperatures. The colder temperatures over here is marked by blue. The hottest temperature over here marked by red. And you'll notice that the colder temperatures hardly flow at all. But as we move towards the hottest temperatures, it actually flows quite easily. And this is also the same of syrup and water, these are things that we use all the time. You notice that hot water, when you pour it, behaves differently. It just even feels differently than it does when it's cold water that you're pouring out of a pitcher. The water is actually slightly more viscous cold than it is hot. And you can recognize that if you pay close attention. Of course, syrup is obvious. You put cold syrup on your pancakes. As soon as they warm up on your plate, because they hit the warm pancakes, the syrup actually starts flowing a lot easier. All right. The other thing that would have a major effect is the composition. So silica content is huge for this. So in this case, this is all a gel that has the exact same composition. The only thing that's changing is the temperature. So it turns out that higher silica content is equal to higher viscosity. So felsic lavas such as rhyolite have very high viscosity. And as a consequence, they're much more likely to explode. Lower silica content rocks have lower viscosities and are more fluid-like in their behavior. So mafic lava, such as basalt, tends to have a relatively low viscosity, and it doesn't explode like a rhyolite will. The other important characteristic is the amount of dissolved gas. So you can have a very viscous magma, but if it doesn't have dissolved gas in it, it's not really a major issue. It's whenever you have dissolved gases, that's the explosion. That's kind of the fuel for the explosion to occur. You need to have the high viscosity and a volatile. So let's talk about dissolved gases. Gas content affects magma mobility. Gases expand within a magma as it nears the Earth's surface as a result of decreasing pressure. So the gases are actually dissolved within the magma. Right, almost like the same way that as we're going to demonstrate in these photos here, carbon dioxide is dissolved in your soda pop, right? So when you open the lid, the bubbles start to come out. The violence of an eruption is related to how easily gases escape from magma. So something that is of very high viscosity has difficulty letting those gases out because it's already sticking to itself and within one another. It also has a tendency to stick to the gas molecules inside in a way. So in other words, it prevents the bubbles from forming, and the prevention of those bubbles from forming cause it to build up that potential energy over time. The amount of gas by weight in some of these most explosive lavas or magmas is 1 to 6%. So it could be a substantial amount by weight. Now, those that are interested in chemistry know that water is a smaller molecule than, say, feldspar, and as a consequence, the weight is not necessarily the same thing as the molar percent. So it has a much higher molar percentage of water and CO2. Those of you that have never taken a chemistry class, just set that aside and don't worry about it. All right, so let's look at the demonstration. This is a fabulous picture. This is a soda pop that is actually exploding. You'll notice that it's got this dark color. It's ejecting out the neck here. And as it comes out the neck, it turns white. Now, the reason why there's a color difference between these two is because of the bubbles. The larger and more numerous bubbles make it take on a creamier color, as we can see here. And so here we see very few bubbles, and it's just starting to expand out a little bit, and then over time those bubbles really take off, and it starts to shoot it up. And here we see these children that are watching an exploding soda, and you'll notice it's all this nice cream color, and it's actually shooting the stuff quite high up into the air relative to the size of the bottle, right? The bottle would be the equivalent of our magma chamber. So this is going to explode a lot of stuff up and out. All right, so now that we've talked about how magmas actually erupt onto the surface and what conditions result in explosive eruptions versus nice fluid eruptions like what we see famously in Hawaii. Let's talk about what that material is once it gets out. And that means we're going to have to talk a little bit about lava and the different types of lava flows that we see. And the most obvious place to start here would be to start with basalt flows or basaltic lavas like we see in Hawaii. Basalt flows are made out of the beautiful black rock, basalt, and they usually come in two varieties. Something called Pahoehoe. Pahoehoe is a Hawaiian term, and it is actually the scientific term also. It's used worldwide. You can go into they don't use the Soviet Union's name anymore, but Russia, and you'll actually hear the word Pahoehoe used by geologists. And Pahoehoe lavas resemble a twisted or ropey texture of surface rock, and it's usually soft and kind of shiny when it first comes out. So this would be a Pahoehoe down here on the bottom. You can actually see the word Pahoehoe flow. By comparison, the Aa lava is this other type up here, and you can actually see this is the one moving out on top. It's got the red glowing material still in it. And this is an flow, again, another Hawaiian term. And this is rough, jagged, blocky texture of lava. And it basically clinks as it moves its way along. Really cool and fascinating stuff. Of the two, of course, this moves much more slowly than this stuff. But compositionally, it's exactly the same. And there's a lot of research about what makes the lava flow one way or the other. A lot of it is still ongoing. Here's another wonderful flow of a Pahoehoe lava, actually, in fact, being formed. Here we can see the lava coming down over this little ridge, and it's filling in this area. And look at these nice ropes, these ropes right here. They look like big piles of ropes piled up. And this is called a ropey Pahoehoe. And this is pretty relatively typical for Hawaii. The local term where there's a lot of Pahoehoe flows with a lot of ropes in it is referred to as Pele's entrails. That's something that is actually used also again by geologists to describe an area. But anyway, you'll notice that there's lava here, but down below, if you look in these little cracks, I don't know if there's enough resolution, you'll actually see that there's still actually lava beneath. So it's not like you could just stand right here. You'll burn your foot off. All right, another kind of cool structure are these things called lava tubes. And lava tubes exist all across the world. And what a lava tube is a lava tube is a natural conduit formed by flowing lava which forms or which moves beneath the hardened surface of a lava flow. All right, so here we can see a lava flow down beneath. There's a geologist up here is carrying an apparatus, probably a thermocouple used for taking the temperature in the lava tube. This is not, in fact, the safest place to be, but it makes for a good photograph, and even the photographer is probably sitting on top of this lava at some point. And this is an area where basically the roof is collapsed. This is something called a skylight, and we can actually look right into the lava tube through the skylight. The reason why it's not the safest place is if it's collapsed right here, it's just what's to keep it from collapsing up here as well. So he is taking, or she, I'm not sure what it is, male or female, is taking a risk, of course, of walking over this lava flow. Tubes can be actively draining lava from a volcano during an eruption, just as we see here. This is from Hawaii. Or it can be extinct. There's a lot of extinct ones, meaning the lava flow has ceased and the rock has cooled and left a long cave-like channel. Lava tubes are likely to exist on previously or currently geologically active planets or moons, including the Earth. So basalt and lava tubes kind of go hand in hand. For example, we know that there's basalt on the moon. We've been there, we visited it, we've collected samples of it, and this is a collapsed lava tube on the surface of the moon right here that we could see. I believe this is actually taken by a telescope, but it could just as easily have been taken by an orbiting spacecraft. Anyways, you can see that there's these little craters all around, and right here, it's all collapsed and formed these little lines. And if you look around, you'll actually see that there's smaller ones. This is actually a huge lava tube. There's smaller ones all over the place. And a lot of people have thought that if we were ever going to colonize the moon, it would probably be by going into these extinct lava tubes, because there's no atmosphere to block the sun or the sun's radiation from doing a lot of damage to us. But these lava tubes would form a natural barrier against the sun. So these rocky planets that have lava tubes, this is something they're looking at very seriously, in fact, for possible space stations or colonization, not only on the moon, but on Mars and any other rocky planets that we might have an interest in going to. Another structure that we see that basalts will form, something called a pillow lava, and they look like these big pillows, right? These things are actually about as big as a body pillow in some cases. They're fairly large. And they form basically on the ocean floor and have elongated shapes resembling toothpaste coming out of a tube. And the reason why is because as soon as the lava hits the surface, it starts to cool right away and it makes a crust. And so these only form underwater. They don't only form in the ocean. It does turn out you can get lavas to form pillow basalts in lakes and rivers and things like this. The main thing is that it has to come up into water. And the main place where we find these pillow basalts, of course, is at mid-ocean ridges. We also find them in the early stages of formation of major island chains that are volcanic. For example, Hawaii. The big island of Hawaii is a big pile of these pillow basalts that would have started at the beginning, at the origination of the island, before it actually started to poke its way out of the land, in which case it started forming these nice lava flows that we see everywhere when we're driving around. Down below, we actually find pillow lavas. Another important texture to understand are these things called pyroclastic materials. Pyroclastic means fire, fire fragment or fire broken. So these are fire fragments, and these are kind of the size of them. So here's some lapillian cinder, and here's some ash. And these are actually just the material that gets shot out of different volcanic eruptions. So an ash and dust is fine glassy fragments. Most of it's either glassy or very fine crystals, very, very small. Pumice is porous rock from frothy lava. Frothy meaning very gaseous, has a lot of gas in it. Lapilli is a walnut-sized material. These are lapilli in here. Here's a quarter dollar here. You'll notice that these things here are probably smaller. These are probably cinder-sized, but these larger chunks over here, as you can see, as zoomed in on this part of the image, is probably closer to a lapilli. This would be a small lapilli, though. Cinders are pea-sized material, so this is about pea-sized, all this material in here. Blocks are hardened or cooled lava. We'll show you some images of blocks, and bombs, of course, are ejected as hot lava. So a bomb is actually lava that is shot into the air. Oh, here it is right here. As a matter of fact, I accidentally moved forward. This is lava that's been shot into the air, and it actually cooled from lava into rock while in the air. And so while it was spinning through the atmosphere, it takes on this football shape. I think this is pretty cool stuff. This is a volcanic bomb. This is what would hit you in the head if you happen to be standing too close to an eruption. These are some of the most dangerous things. Not only does it hit you in the head or hit you in the body, it's also still barely cooled off. Remember, when it comes out, it's molten. By the time it hits you, it's rock, but it's still several, maybe 800 degrees Celsius, 900 degrees Celsius. And so some of the victims who have actually survived being hit by volcanic bombs have also suffered extremely bad burns. This is a relatively small bomb, actually. Here's a 1 inch right here. So this whole thing across is about 5 inches or whatever. If it was to hit you in the head, it would kill you, of course. But they get much, much larger. I personally have seen lava bombs as long as about 2.5 feet out in the Mojave Desert, and I know that they get larger than that even. So just because it's a basalt that's ejecting out of a volcano doesn't necessarily mean it's something you can come up and not worry about too much. If it starts spattering any lava out, you need to get away as quickly as possible, or you're going to be running the danger of being hit in the head by one of these football-shaped rocks. All right, so let's talk about the anatomy of a volcano. What is it that makes the volcano structure up? And it depends, of course, on the kind of volcano. So we need to be aware that there's the opening of the summit of a volcano. The smaller summit is called a crater. So here's a volcano. This is a volcano called Wizard Island. It's a type of cinder cone, and right at the top is this little hole, and you can actually see it. Here's an aerial photo of it. There's a little hole up there. That's the crater. That's where the explosions would come out in the event of an eruption. Same thing up here. This is the same image, except this has got the water missing from it. Okay, and it's generally less than 1 kilometer in diameter. Wizard Island is actually much smaller. This is maybe, I don't know, 60 feet across, which is about 20 meters. So that's much smaller than 1 kilometer. So that's definitely a crater. And you'll notice that there's little pit craters and cinder cones and things like this down here at the bottom, actually at the bottom of this lake. This is Crater Lake, by the way. I should have mentioned that right at the beginning, in Oregon. Now, a caldera is a summit depression, typically greater than 1 kilometer in diameter, produced by collapse following a massive eruption. Well, I've been showing you these little volcanoes here in the middle of Crater Lake, but the reason why it's called Crater Lake isn't because of the craters, not the small ones. It's because this entire structure from side to side, notice how round it is one giant crater. It is much larger than 1 kilometer in size. So these are little volcanoes that reside within the central blasting area of the main volcano. And this is actually, in fact, a giant caldera. These are just little blisters that came up after the last eruption. So that last time that Crater Lake exploded, it blew all this material out, made this huge caldera. And since then, small little volcano, almost like blisters, have kind of come up and filled in some of the parts. But the main volcano is still very, very, very dangerous. And it's this huge caldera that has formed since the last eruption. And so all this material would be shed out in every direction. Um, and we can actually map out the last eruption deposits. And this was a huge eruption, very dangerous if it was to happen today. All right, so a vent is just an opening connected to the magma chamber via a pipe. So over here, you'll notice that there's another little peak over here. It turns out that the magma chamber that's underneath Crater Lake that created this huge chamber has several pipes that connect off to the side. Probably the most famous one, if we were to go back to, say, Hawaiian geology again, the most famous pipe would be connecting into the Pahoehoe vent, which is connected to Kilauea. So in a way, it is actually a Kilauea eruption. It's just that the lava is coming out of a side vent rather than out of the main crater, or the main caldera, I should say. All right, so let's talk about the different kinds of volcanoes. So let's stay in Hawaii because we have the best examples right here in Hawaii to demonstrate. So the best shield volcano to ever demonstrate in any of these examples is always going to be Mauna Loa, and this is what we have a picture of here is Mauna Loa. It's basically a broad, slightly dome-shaped, and here you can clearly see it's slightly dome-shaped. This is a really tall mountain, over 14,000 feet. Very, very tall. But it's so large that the side flanks of it make the entire mountain actually look like it's not very tall. It's actually one of the tallest mountains in the continental United, or in not just the continental United States, the United States in general, all 50 states. Okay, it's generally composed primarily of mafic, which is, say, basaltic lava. Whenever you hear mafic lava, you should immediately think of basalt. And it generally covers large areas. Shield volcanoes do exist in other areas, but Mauna Loa is the heart of the Big Island of Hawaii. It covers a massive area. Produced by mild eruptions of large volumes of lava. When they say mild, they mean non-explosive. It doesn't mean that there aren't occasionally explosions that occur on shield volcanoes. In Hawaii in 1924, there was a very large eruption that occurred in Kilauea that actually killed somebody. But compared to Mount St. Helens, it's relatively small. Mauna Loa on Hawaii is a good example. So this is a picture of Mauna Loa, and I believe it's a picture that's taken from one of its sister volcanoes. I believe this is a picture from Mauna Kea. In contrast with Mauna Loa, we have Mount Baker. Mount Baker is something called a composite cone or a stratocone. Okay, so we'll notice that Mount Baker, by comparison, has this nice tall peak. And it's really kind of hard to identify a summit crater. If you were to actually look at Mauna Loa, go up to the top, you'll find that there's actually a summit crater in a lake, not all that different than what you see at Crater Lake. It's a lot smaller lake than Crater Lake is, but you get the idea. There is, in fact, a large crater up there that you can go and visit. Here, it's a little more difficult to see the crater. It's present, but the problem is that it's covered in snow. A lot of these volcanoes, in fact, are so tall that they're constantly covered in snow. And the vegetation usually has a hard time growing because of the snow. The snow will form glaciers, and the glaciers will strip off all the vegetation. So you'll see forest here, but you won't see much in the way of forest here. On top of that, there's not poisonous gases and stuff that come out of the soil and kill all the vegetation as well. So most of these composite cones, or these also called stratocones, and this is what I actually like to use is the word stratocone, are located adjacent to the Pacific Ocean. You know, Mount St. Helens is probably the most famous American example, though Mount Baker is also very famous. Mount Mammoth in eastern California is another famous one, as well as Mount Lassen, which erupted at the beginning of the last century. They're large, classic-shaped volcanoes. So when people think of dangerous volcanoes, this is usually what they think about. And there's thousands of feet high and several miles wide at the base. So they can be large peaks. They can actually look just like ordinary mountains. And sometimes we
take a while to figure out that they in fact are volcanoes. In fact, Crater Lake wasn't even determined to be a volcano until a long time after it was discovered. Why are they called composite cones or stratocones? It's because they're composed of interbedded lava flows. In other words, not a single lava flow, but interbedded. It means more than one of different types. So lava flows and layers of pyroclastic debris. So here's a picture of Mount Baker. This was a mountain that people were afraid was going to explode in the 1970s, and it turned out it didn't do anything. It was one of the reasons why they were not prepared for Mount St. Helens, because they saw a lot of activity in Mount Baker, nothing happened. Then they saw similar activity in Mount St. Helens, and then it blew up. So you can see that volcano science at the time was still being worked through, and in fact, we're still working on a lot of these problems. So let's look at the kind of the blood and guts of one of these stratocones. So this is a good picture, actually. So there's a magma chamber down below the stratocone. If you remember from the last lecture, the large shield volcanoes have their magma chamber actually up inside the volcano. But in the stratocones, it's usually down below, and the conduit is far below the volcano. Okay, so here's the magma chamber that feeds the stuff up. And when an eruption occurs, there's usually two stages. The first stage is one where a lot of ash will come out and a lot of bombs will be thrown around. Pyroclastic material, fire-broken material, will form in the very first start of this eruption as the gases are trying to come out. Now, the later part of the eruption will be mainly lava flows that aren't exploding. And the reason why they're not exploding is because the gas by that point has already left the magma chamber. So you get layers of pyroclastic material covered by lava, pyroclastic material covered by lava, back and forth, up and down. And each one of these couplets of this pyroclastic material and lava is usually interpreted to be a single eruption or a series of eruptions over a period of time. And so we can actually study these things by looking at the layers within the volcano. Notice the volcano, as the layers move away from the volcano, they get thinner. That makes sense. Okay. So that's something important to notice. And the word strato, by the way, means layered. So here's a composite volcano or a stratovolcano, which is a layered volcano. So let's talk a moment about composite cones, because these are really important to understand. The most violent type of activity that we routinely see on the planet is the composite cones. There's a lot of them, and they're constantly erupting somewhere on the planet. The most famous example is Mount Vesuvius in Italy, which did a lot of damage during the 1st century AD. They often produce pyroclastic flows. Now, the pyroclastic flows aren't just these clouds that come out. This is a pyroclastic flow here. But there's something about these pyroclastic flows you need to know. It's not just a cloud of dust. Pyroclastic flow is made of hot gases infused with ash and other debris. Now, ash is actually little tiny particles of pointed glass that are made in the magma chamber while it's exploding. It's very dangerous stuff. And what will happen is, as the volcano erupts, it'll push all this ash up into the air, but the ash, being heavier than the air around it, will then fall back down on itself and create these pyroclastic flows that run down the side of the volcano. That's what this is here. They could be several hundred degrees Celsius. They can be very, very hot. So if it hits you, you die from this hot, glassy material getting stuffed in your mouth at very high speeds. It's actually a terrible way to go. It moves down the slopes of a volcano at speeds of up to 200 kilometers per hour. That's about 120 miles per hour. You can't outrun them. If it hits your house, it will just incinerate your house in a few seconds. They're very dangerous. In addition to that, after you have your pyroclastic flow distributed across everywhere, it leaves a layer of ash all over everything. The ash causes cancer. It's bad stuff. But it also means that you can produce something called a lahar. A lahar is a volcanic mud flow. So in this case, this is a lahar that has come off of a volcano, and what's happened is the lava has come up and injected some heat into the area and melted the snow at the top, the snow cap that's at the top of a lot of these volcanoes. Let's go back to Mount Baker, which is back here. See all this snow up here? Imagine if you put enough heat right underneath there, this whole thing would melt in a very short period of time. There's a lot of water up there. And so that's what's happened here is basically a lot of heat has come up here, melted this, and a lahar, which is basically a combination of this glass or this volcanic ash and pyroclastic material, will come rushing down the mountain at very high velocities. And I will tell you that mud flows are deadly compared to floods. Floods, I would rather be hit by a flood any day of the week, just pure water. But if you get hit by a mud flow, the chances of surviving it are relatively poor. Okay, and there are cases in the Andes Mountains where a composite cone basically wiped out entire villages and killed thousands upon thousands of people in a single moment. It's a really bad way to go. Just one more note on the lahar. Another reason why they are so dangerous is you actually don't need an eruption to generate a lahar and kill these thousands of people. The one that occurred in the Andes Mountains actually was generated and nobody even saw it coming. They all died in their sleep. So this is a iconic image of a pyroclastic flow. Notice the Jeep down here. These people are actually running down the road. This is a pyroclastic flow from Mount Pinatubo, which is in the Philippines, and it very seriously threatened the city of Manila, I believe in the late 80s. Extremely explosive series of eruptions. But fortunately, through proper planning and through lessons learned from Mount St. Helens and Mount Baker and some other ones, Filipino geologists actually were very good at making some predictions as to whether or not the Mount Pinatubo was going to explode and evacuated the proper areas. That didn't mean that people weren't killed from basically lahars and some other things that went on, but the main eruption, at least they could see it coming and they were prepared for the most part for it. So anyways, here we see a pyroclastic flow, and look at how large this thing is. It probably came in at 100 kilometers per hour, maybe 150 kilometers per hour. It's going to incinerate everything in its path. It's a really frightening experience. It's a scary thing to have to run from. Here's some less fortunate people. These are people that were killed by Mount Vesuvius. This was the volcano I mentioned a little earlier in this lecture. And essentially what happened is they were sleeping in this location, and these people were covered with ash, and basically the casts of their bodies were preserved. And we've been able to go back and clear out the ash, and we found inside these holes what is the remains of people. We found people, and we found jewelry and some other things, but these were people that were lying here at this position, this person here getting burned while actually sitting up. And basically it comes in, it's so hot that the water in their body flashes to steam and it quenches or cools the lava right around them. And it creates a shell of their body. And that's what this is right here. It's really a bad way to go. They were sleeping and they were done. One of the most famous eruptions in history is at Pompeii. All right, so there's another important structure we should talk about, this thing called a lava dome. So this is Mount St. Helens today. Mount St. Helens had erupted. This whole side of the mountain had literally fallen off and exploded outwards. It killed almost 50 people, or it might have even killed more than 50 people, about 50 though. And since then, the lava didn't stop coming up, but even though the eruption stopped. What has happened since then is the lava has actually plugged the hole in something called the lava dome. So even though this was originally a big crater, there was nothing here. In the last 35 years or so, a big thick plug of andesite has come up and filled this hole. It's very thick, it doesn't want to flow, it's very resistant, and as a consequence it's formed this little blister here, and it's called the lava dome. Now this lava dome is something we have to watch out for, because if it gets too tall, it will actually collapse and a pyroclastic flow will come down here across the valley and do tremendous damage. We need to be careful of that. But also, if it was to go ahead and remove that lava dome through, say, a landslide or a pyroclastic flow, it would reduce the pressure on the magma chamber below, and you could actually create another explosion. So we have a lot of things to be very nervous about at Mount St. Helens. And this is one of the volcanoes that are being very closely watched, because it can re-erupt at any time. Provided enough magma was to come up into the magma chamber and decompression was to occur. So there's a third kind of volcano that is extremely common. These exist in almost all parts of the world. They've been discovered even in Antarctica. And these things called cinder cones. And cinder cones are basically these little volcanoes. These are trees. This is nowhere near as large as Mauna Loa or Mount St. Helens or Mount Baker. As a matter of fact, here's some more cinder cones down here. And you can see the local mountains are much larger. These things you could probably climb in 15 minutes, if at most, maybe 10 minutes. And they're little volcanoes that they go off for a very short period of time, and then once they're done, they're done. They usually don't repeat over periods of hundreds or thousands of years. This volcano here in Mexico, I believe it started to erupt in the 1940s, and it erupted, I think, over a period of 8 or 9 years, and then it's been quiet ever since. It hasn't done anything. Notice that the lava flows came out, and one of the last stages it did was it piled up all this scoria or all this cinder all around it. And that's why it's called a cinder cone. Compared to the other types of volcanoes, they tend to have steep slope angles. Notice how steep that is. It's not very tall, but it's very steep compared to Mauna Loa with these big, large shield volcanoes. This is a really steep surface. And they tend to be rather small in size. The largest one I've ever seen is Sunset Crater in Arizona, which I have a cross-section showing about how big that is relative to Mauna Loa here in a moment. And they frequently occur in groups. So here's a cinder cone in the desert here, another one located next to it, and I assure you there's actually several more that are outside this field of view. In Hawaii, it's not uncommon to find 7 or 8 cinder cones all nested together on one little area. Where I'm currently recording from, as a matter of fact, I walk out in the morning, I can look up onto the Kohala volcano, and I can see at least 7 cinder cones completely covered in grass and that have not erupted in probably 12,000 years, but they're there nonetheless. All right, so like I promised, here's some size comparisons of 3 types of volcanoes. So here's Mauna Loa, right? Look at the size of this thing. Extending all the way across. The caldera is way up here at the top. The magma chamber is actually right here somewhere in the middle of the volcano. There's actually another magma chamber probably down below somewhere. Volcanologists are always working out what they think is happening. By comparison, here's Mount Rainier, which is a composite cone, not all that different from Mount Lassen or Mount St. Helens. And it's big. Without a doubt, it's big, but it's not as big as these giant shield volcanoes like we see at Mauna Loa. And of course, the smallest of them all is these cinder cones, Sunset Crater in Arizona, which is a very large cinder cone. But by comparison with these two, it's just a little blister. It's just a little tiny thing by comparison. The last landform that I think is really fascinating, because we see them all the time in nature, and we tend to wonder why in the world there's this beautiful column of rocks sticking up into the air. They're basically, this material here is actually the central part of an old volcano that's been eroded away. And it's basically an old volcanic pipe. So a volcanic pipe and volcanic necks are resistant vents left standing after erosion has removed the volcanic cone. So here we have an old magma chamber, an old conduit, a pipe that once resulted in the distribution of a volcano, maybe a stratocone, maybe a composite cone, or a cinder cone. And over time, when nature is working on this, it basically is able to erode everything else away. But the hard part of the heart of the volcano is the last thing that remains. And so this is 1,700 feet. This would not be, in fact, a cinder cone. This is almost certainly a composite cone, a very large and powerful volcano was almost certainly residing here at one time, and this is the last part of it before it finally went dead and began to erode. So anyways, we've kind of covered all the different volcanic landforms, how they erupt, what makes an explosion occur. A lot of information, but volcanoes are fascinating, and it's a whole field into itself. Anybody that studies geology at some point will be tempted to take a class in volcanology. And I think that anybody that's taken this class would be actually well prepared to just go and take one over at the local university and learn a little bit about volcanoes. They actually should have enough information from this course. So with that said, I hope that you enjoyed this lecture on volcanoes, and we're going to begin talking about a whole new cycle, part of the rock cycle, sedimentary rocks, in the next video. Until then, I wish you the best. Goodbye.